Welcome back. It's another Physics 142 video, and in this video I want to give another example of using the Biot-Savart law to calculate magnetic fields. We've been talking about the fact that little pieces of current, little bits of current, that is little bits of moving charge, create magnetic fields, and we realized that the way that we can calculate the strength of those magnetic fields and their direction is through this law, the Biot-Savart law, which I've written up here at the top. And we've done a couple of different examples so far. We did an example where we had a loop of wire, or a circle of wire, and we realized that the magnetic field at the center of that loop of wire ended up being equal to mu naught times the current divided by 2 times the radius of the circle, and was coming directly out of the center of the circle, perpendicular to the circle. We also did a result with a piece of wire, and we were at the center of a piece of wire, and we realized when we extended the wire really far up and really far down, we got this result that for a very long wire, some people talk about an infinitely long wire, but it just means any case where the wire is a lot longer than the distance you are to it, where you're a lot closer to the wire than the length of the wire, you get this result, mu naught I divided by 2 pi r, and we realize that the magnetic fields wrap around that wire. So if you have some wire, like my pen here, the way to get the direction of a magnetic field for that wire is to put your thumb along the wire and then to curl your fingers. This would be with your right hand, and whatever way your fingers curl, that's representing the magnetic field. So that would mean on this side, the magnetic field is coming up out of the page. On this side, it means it's going down into the page, right? On the top, it would be going to the right, and underneath the wire, it would be going to the left. So we found that magnetic fields loop around wires. So that those were 2 results that we did in previous videos. In this video, I want to think about a more complicated setup then, where we start combining some of these results and see what we can learn. So the example that I'm interested in thinking about here is this example that I've drawn, and in this picture we have a wire that's coming in here from the left. And the wire is a straight wire for a while, but then we bend it in a half circle here. So I've bent the wire in a half circle, and then I have another straight wire emerging, going up to the top there. So we have sort of 3 separate parts that we would want to think about with this wire. And what I'm interested in is, what is the magnetic field at this spot P, right at the center of sort of the half circle there? All right, what's the magnetic field at that spot P? And so to approach this problem, the sort of key new insight is that if you have a more complicated setup, it's useful to break that setup into pieces that you can calculate more easily. So for this particular problem, I would suggest breaking this up into sort of 3 different pieces, right? We have a piece of the wire coming in from the left, and we're thinking of this as a really long wire coming in from the left, all right? It's coming in from very far away to the left. So I would call this part of the wire, I'd call this maybe piece number 1 here, right? We have piece number 1 is this part of the wire. Then we have sort of the half circle, and everything's going to be sort of similar along that half circle, right? Everywhere along the half circle will have sort of a similar perspective related to point P. So let's call this part 2 here. And then once we get off the half circle and we're on another wire, well, this is, again, a very long wire going up to the top. Let's call this part 3. And so what we'll need to do to get the magnetic field at point P is we'll need to compute the magnetic field at P from this first bit of wire, the magnetic field at P from this second bit of wire, and the magnetic field at P from the third bit of wire, and add them all together, right? Basically, the magnetic field is the magnetic field from every little piece of the wire, right? So we'll want to add all of them together. So we should get our total magnetic field, right? Our total magnetic field should then be the magnetic field from part 1 plus the magnetic field from part 2 plus the magnetic field from part 3, all right? So let's sit down and compute these parts and see what happens. So, or maybe stand up, whatever it suits your fancy for how you solve Biot-Savart problems. I'm currently sitting, but maybe I should stand up. I don't know. Anyway, okay. So part 1, how do we do it? All right, so we're interested in finding the magnetic field from part 1. Well, we know that we need to use the Biot-Savart law to do it, right? And so we write down that it's the integral over that wire of mu naught over 4 pi times I dl cross r hat divided by r squared, the magnitude of r squared. And so sort of the first thing that we need to do when we deal with a Biot-Savart problem is we need to deal with this cross product. So that means we need to draw in some dl's and we need to think about what r hat is. All right, so to draw in some dl's, maybe I'll do that in green here, right? So for this first little bit, let's think about just a little piece of wire, if you have current going to the right here, then I would draw this little piece of wire. It has a length dl, and I would say that it's going in that direction of the current to the right. So this is my little dl vector here. All right, there's my little vector dl. But then I also need r hat, right? I also need r hat. And r hat is a vector. Well, r is the vector that runs from my little spot dl all the way to point P, right? So if I was to draw an r, it would be this whole vector right here. That would be r vector, right? R hat is just the unit vector, the vector of length 1 that points in that same direction, right? So r hat, if I was to just draw r hat, it has just length 1, but it's pointing in that direction. So this vector right here, that's r hat, right? So now we need to take the cross product between dl and r hat, right? And remember, the cross product involves taking the magnitude of dl and the magnitude of r hat, which is 1, and the sine of the angle between them. Well, and what's the angle between them here? Well, they're going the same direction, so the angle between them is 0, right? And so the sine of the angle between them is also 0. And so we get a big 0 right here, which means that this whole integral from 1 must be 0, right? And that sort of makes sense, right? Like magnetic fields always, if the magnetic field is in, or if you're looking at a spot that's in the same direction here, right? There's nothing crossing here, and so you don't get any magnetic field, right? Magnetic field, we know, loops around wires. It's not off the end of wires. So from part 1, we just get 0 because the r hat and the dl are in the same direction, all right? So that's B1. All right, what about the magnetic field then from part 2? Well, again, we write down the Biot-Savart law, mu naught over 4 pi, I dl cross r hat over r squared. And again, we need to write in some dl's. So let's pick a little dl vector here, right? So I take a little chunk of this wire. I'll draw in a dl, right? It's going in the direction of current flow. All right, there we go. And so if this is my dl vector, well, then what's r look like? R is the vector that goes from dl to point P, right? And so r hat must just point along there. So this is r hat for part 2, right? And so now if I do this integral over here, right? Let's write this integral mu naught over 4 pi times I, and then we need to do the cross product, so that's dl times the magnitude of r hat, 1, times the sine of the angle between them, and the angle between r hat and dl here, we can see, well, along a half circle, they're perpendicular, right? So that's 90 degrees. So sine of 90, and then, well, what's the radius? The radius is the radius of the circle, right? What's the distance, right? R is the distance from my dl to the point P, and so what's that distance here? Well, it's the radius of the circle, that's capital R. So we'll plug in capital R. squared. And then now we want to compute this integral. Mu naught is a constant, 4 and pi are constants. The current at every spot in this wire is the same, so that's also a constant that can come out. And the distance every spot along the curved part of this wire is from the center is the same. So r is also a constant, so that can come out. So we get mu naught I over 4 pi r squared, big R squared there, times the integral dl times 1 times sine of 90 is 1, so just the integral of dl. And well, what's the integral of dl here? Well, it's over half a circle, right? So this is going to be half of a circle. And so what is half of a circle? Well, the circumference of a circle, remember, is 2 pi r. And so half of that, just divide by 2, is going to be pi times r, right? And so if we write this all out, then we're going to get mu naught I times pi times r divided by 4 pi r squared. And it looks like we get pi's that cancel and one factor of r that cancels. And so that becomes mu naught I over 4r. And we need a direction here, right? Well, what's the direction going to be? Well, let's see. If we're doing dl cross r hat, right? dl, need to adjust it a little bit here, right? dl is going this way, r is going that way, so my thumb is pointing out of the page, so that means p is coming out of the page, and that makes sense. If I curled my fingers around this wire, right, my fingers would be coming up out of the page at spot p, so out of the page. And hopefully this makes some sense. If we go back when we did a full circle, we got mu naught I over 2r, and here we got mu naught I over 4r, so half a circle is contributing just half the magnetic field. I think that makes a lot of sense. All right, well, we've got 2 parts down. Let's do the third one, all right? B3 then, all right, B3. Again, we'd write down the Biot-Savart law. And here, I'm just going to actually, rather than go through it all, use the reasoning. We found that when we use half of a circle, right, we just got half the magnetic field because we only had half of the DLs contributing, right? Half the little pieces of current contributing. Similarly here, before we did a wire, we did a really long wire, and we were thinking about being at the middle of that wire, right? And we got the result, mu naught I over 2 pi r. Well, here we could think of point P, that's sort of at the end of a wire, right? It's a really long wire, but we only have half of the wire. Right now we only have half of the wire, so this is what we might call a half infinite wire, all right? And a half infinite wire is only, again, contributing half of the DLs, right? Half of the DLs, half of those little, magnetic charges, if you will, right? Those IDLs. So you're only going to get half of the magnetic fields. So B3 is going to be 1/2 of an infinite wire. All right, B3 is half of an infinite wire, all right? If we think about our DLs, right, the DLs, let me draw on a DL here. All my DLs are along the wire here, right, DLs. And all of my R hats are going to be pointing, sort of this-ish direction, right? There's my R hat up here. Be a little more like that. So all of my DLs will be this way. All my R hats are going to be somewhere over here. So this is always going to, again, be create a magnetic field that's out of the page over at point P, right? You can see my thumb is pointing up out of the page. That also makes some sense. If I put my finger along the wire and curl my fingers at P, my fingers would be coming up, right? So the direction is going to be out of the page. And so what's half of an infinite wire? Well, half of an infinite wire is mu naught I over 2 pi r was one infinite wire, so half of that. So we need 1/2 of, let's give just a little more space, make sure everybody can still see here. Yep, we're doing okay. 1/2 of mu naught I over 2 pi r is going to be mu naught I over 4 pi r out of the page. All right, so then to conclude here, we need to add up all three of these, right? So we had 0 for B1. We had mu naught I over 4R out of the page for B2. Mu naught I over 4R. And then for B3, we got mu naught I over 4 pi R. Mu naught I over 4 pi R. And so if we add all of that together, then, I could combine terms here, I guess, a little bit. It's mu naught I over 4R times 1 plus 1 over pi, right? And this is out of the page, right? Both those were out of the page, and so we added them, right? If one of them was an into the page for some reason, then we would have had them going in opposite directions, and we would have had to subtract them. So hopefully this shows you just a little bit. If you have a more complicated setup, use what you know, break it into smaller chunks, lines, circles, that kind of thing, and then you can use the fact that all of those magnetic fields combine together, that there we have sort of a superposition of magnetic fields, you might say, to find the total magnetic field.